Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. This presentation will discuss the Carolina Bays as evidence of a cosmic impact, and in particular, it will discuss the glacier ice impact hypothesis, which is derived from the characteristics and the mechanism of formation proposed for the Carolina Bays. The Carolina Bays are marshy, shallow depressions with sandy rims found along the eastern seaboard of the United States, primarily in North Carolina, South Carolina, and Georgia, but they are also found in northern Florida, Virginia, Maryland, and as far north as New Jersey. The bays were known to the first settlers of the United States, but it was only with the development of aerial photography in the 1930s that their characteristic elliptical shape and their northwest to southeast orientation gained attention and became the subject of speculation about their origin. The invention of LiDAR in the 1960s combined laser focusing with radar's ability to measure distances. The technique made it possible to create very precise topographic maps which recorded small differences in elevation. When applied to the east coast of the United States, LiDAR found thousands upon thousands of Carolina bays. It is estimated that there are at least 500,000 Carolina bays along the coast. The bays are enormous. The small rectangle in the center of this image is a pig farm with 9 buildings. These are shown in more detail in the inset on the right. Each of the large buildings is over 100 meters long, or about the size of a football field. On the east coast of the United States, the Carolina bays can occur at elevations as high as 200 meters, or 650 feet above sea level. This image is centered approximately 25 kilometers, or 15 miles, southwest from Fayetteville, North Carolina. The color gradient is used to represent the elevation. The lower right corner corresponds to an elevation of 16 meters above sea level, and the upper left corner corresponds to 75 meters above sea level. Interstate Highway 95 can be seen as a thin line going from the top right corner toward the bottom. The flow of water toward the sea has eroded many Carolina bays. This image shows the channels of many streams and rivers. The land surface near Tatum, South Carolina, is densely covered with Carolina bays. This area has many examples of well-defined bays, although many of them have lost their sharpness due to erosion. The bays near Tatum have the typical features which pose 4 questions that a theory of bay formation must explain. Number 1. Why do the Carolina bays have elliptical shapes with a specific width to length ratio? Number 2. Why are the bays oriented with their long axis pointing in the same direction? Number 3. Why do the bays have elevated rims? And finally, number 4. What mechanism could have produced the overlapping bays? Carolina bays occur in sandy, unconsolidated ground close to the water table along the Atlantic seaboard, but similar bays are also found in Nebraska and Kansas, where they are called rainwater basins. The bays in these Midwestern states differ from the ones in the East Coast in that their major axes are aligned from the northeast to the southwest, almost perpendicular to the orientation of the East Coast bays. Projections along the length of the Nebraska bays and of the Carolina bays intersect around the Great Lakes, hinting that whatever created the bays radiated from the Great Lakes region. The bays in Nebraska occur at altitudes of 400 to 900 meters above sea level, which is about 1,300 to 3,000 feet above sea level. The sandy soils of Kansas and Nebraska once were the shores of the western interior seaway of North America, which disappeared by the Paleocene epoch 60 million years ago when the Laramide orogeny uplifted the Rocky Mountains region. These bays near the geographic center of the United States are 2,000 kilometers away from the Atlantic and Pacific Oceans. Fewer bays can be seen in the Midwestern states because only the larger bays have endured the erosion by rain and the accumulation of layers of windblown dust and silt. This is a summary of the Carolina Bay characteristics. The Carolina bays are elliptical and occur only in unconsolidated sediments. The bays are oriented with the major axis radiating from the Great Lakes region. The major axis range from approximately 60 meters to 11 kilometers. That corresponds to about 200 feet to 7 miles. The bays are shallow depressions with a maximum depth of about 15 meters. Rim heights vary from 0 to 7 meters. Many bays have elevated sandy rims which are higher at the terminal end. The deepest portion of any bay is also at the terminal end. Small bays frequently overlap or are contained in bigger bays. The soil layers or stratigraphy beneath the bays is not distorted. No bays occur on modern river floodplains or beaches. The bays occur on terraces of different geological ages and at different altitudes. The Carolina bays have a wide range of sizes. This graph displays the frequency of the various sizes of bays from a survey of approximately 500 bays. The graph was produced by Michael Davies, who has a website featuring LiDAR images of the Carolina bays. In this graph, we can see that bays with major axis of 220 meters and minor axis of 160 meters are the most common. That corresponds to bays of about 720 by 525 feet. From the distribution curve, we can calculate that approximately 65% of the Carolina bays have major axis smaller than 440 meters. The graph helps to put things in perspective. Bays which are larger than 1 kilometer are very prominent in the LiDAR images, but they comprise only a small percentage of the total number of bays. One of the most striking features of the Carolina bays is their perfect elliptical shape. This slide shows the geographical coordinates of several Carolina bays with measurements of the major and minor axis, also called the length and width of the bay. The calculation of the width to length ratio and the eccentricity yield very consistent values for bays of different sizes. In general, the width to length ratio of Carolina bays averages 0.58 and the eccentricity averages 0.81. This table includes 3 Nebraska bays, which are indistinguishable from the bays in the East Coast on the basis of their geometrical characteristics. The only way to tell them apart is to look at their longitudes. One of the first proposals for the formation of the Carolina bays was made by Melton and Shriver from the University of Oklahoma in 1933. They suggested that a meteorite shower or a colliding comet coming from the northwest could have created the bays with their peculiar alignment. Their suggestion was largely dismissed because at the time geologists did not favor any extraterrestrial hypothesis. Terrestrial surface structures created by impacts only became accepted around 1960 when geologist Eugene M. Shoemaker presented criteria for establishing that Meteor Crater in Arizona was the result of an extraterrestrial impact and not the caldera of an extinct volcano. Using the principles established by Shoemaker, scientists concluded that the Carolina bays could not have been created by an asteroid or comet. Analysis of the Carolina bays showed no evidence of a hyperspeed impact such as shattered cones, crystals displaying shock metamorphism, meteorite fragments, or the occurrence of siderophile elements, which are chemical elements such as iridium that are more common in meteorites than in the Earth and which were present in the impact that killed dinosaurs. Extraterrestrial impacts would have melted the target material, and impacts large enough to create the bays would have penetrated the soil, excavated bedrock, and produced distinctive signs of intense disturbance in the bedrock. The fact that there is no bedrock ejecta around the bays excludes the possibility that they were formed by extraterrestrial impacts. In 2007, Richard Firestone and several co-authors proposed that an extraterrestrial impact 12,900 years ago caused the late Pleistocene megafaunal extinctions and the Younger Dryas cooling event, which was a cold period that lasted approximately 1,000 years. Firestone proposed that a comet airburst could have killed the mastodons and saber-toothed tigers that lived in North America toward the end of the last ice age and triggered the cold event. A few Carolina bays were examined to obtain impact spherules and nanodiamonds that were supposed to prove that a comet airburst had occurred. Firestone extended his argument in another publication in 2009 by pointing out the radial orientation of the Carolina bays. He proposed that the comet impact could have struck the glaciers that covered North America and that fragments of the comet could have created the Great Lakes instead of an impact crater. He also suggested that the ice ejected from the collision could have formed the base, but he did not explain exactly how. Firestone's hypothesis, which was dubbed the Younger Dryas impact hypothesis, was soundly rejected by the scientific community. Nicholas Pinter and other impact experts wrote a scathing requiem paper criticizing Firestone and his colleagues for not providing the type of impact evidence established by Shoemaker for hypervelocity impacts. The claim that the Carolina Bays could be used as evidence of an impact was also rejected because there was no crater from an extraterrestrial impact and the bays had different dates, which meant that they could not have been created by a single event. The Requiem paper was to symbolize the death of the extraterrestrial impact hypothesis. Without being able to resort to extraterrestrial impacts as the origin of the Carolina Bays, geologists started to propose theories like substrate dissolution and marine waves and currents that reduce the volume of karst-like depressions, which are later modified by wind or ice push processes. The bays have also been characterized as thermokarst or thaw lakes that are circular or elliptical in shape and are often aligned with the prevailing wind. Thermokarst lakes form when underground ice melts in a region underlain by permafrost and the ground collapses like a sinkhole. The problem with this terrestrial formation hypothesis is that they do not provide a mechanism for the formation of elliptical bays with raised rims whose axes are aligned to radiate from a common point, as is necessary to account for the orientation of the Carolina Bays. In addition, the wind and water processes fail to explain how bays at elevations of 200 meters or higher could have formed on ground that had not been close to the sea for millions of years, or how the prevailing winds from the northwest in Nebraska could have created bays almost perpendicular to the wind direction. None of the proposed ideas for terrestrial processes has been accompanied by a physical or computational model to explain why the Carolina Bays have elliptical shapes with width-to-length ratios and eccentricities that are within a very narrow range. This slide illustrates thermokarst lakes in Alaska and Russia. These lakes form when underground ice melts in a region that has permafrost and the ground collapses like a sinkhole. The cavities fill with water forming lakes, and the shape and alignment of the thaw lakes is determined by the contours of the land. The alignment, if any, is generally in the direction in which water drains toward lower elevations. Unlike the Carolina Bays, thermokarst lakes are not perfect ellipses, they have no overlaps, they have no preferential rim thickening, and they do not have raised rims. The salt lakes in Western Australia share some visual similarity to the Carolina Bays. The Australian salt lakes formed when marshy ground dried up, leaving oval pools along the landscape. However, the drying process does not create the raised rims or overlapping ellipses which are characteristics of the Carolina Bays. The most popular explanation of the origin of the Carolina Bays involves a combination of wind and water processes. According to Mark J. Brooks and his co-authors, the Carolina Bays formed during the Pleistocene epoch, starting as shallow lakes along the Atlantic coastal plain from New Jersey to Florida. The distinctive shape and northwest to southeast orientation of the bays developed through stronger than present southwesterly winds blowing over water-ponded and shallow depressions. The depressions were expanded and oriented by wave erosion, resulting in bay elongation perpendicular to wind direction and the formation of peripheral, downwind sand rims and shorelines on the eastern and southeastern margins. The dates of formation of the Carolina Bays have been measured using optically stimulated luminescence, or OSL, which estimates the time since last exposure to sunlight for quartz sand and similar materials. This image shows Big Bay in South Carolina. According to Brooks, Big Bay formed from wind-driven sand sheets from the Wateree River, which is 10 kilometers to the west. The sand moved across Big Bay about 74,000 years ago and was resurfaced subsequently 33,000 to 29,000 years ago. The innermost sand rim at Big Bay was remodeled as recently as 2,200 years before the present. Although the wind and water processes seem plausible, they are not applicable to the bays in Nebraska, which are at high elevations and have been far from the sea for millions of years. The wind and wave model also lacks a mechanism for constraining the elliptical shapes of the bays to the observed aspect ratios, and there is no explanation of how the overlapping bays are formed. The Requiem paper by Pintner established with great certainty that the Carolina bays could not have been created by the hypervelocity impacts of extraterrestrial projectiles. In addition, the great span of dates measured for the Carolina bays seemed to preclude the formation of all the bays by a single event. The glacier ice impact hypothesis addresses both of these constraints by proposing that the Carolina bays were created by impacts of terrestrial glacier ice at ballistic speeds of 3 to 4 kilometers per second, and by pointing out that the dates obtained for the Carolina bays reflect the age of the terrain on which the bays are found, but do not correspond to the time when the bays were formed. The glacier ice impact hypothesis uses geometrical conic sections to model the Carolina bays. The elliptical bays are produced when oblique conical cavities intersect with the level surface of the Earth. This is basically the mathematical definition of an ellipse, an intersection between a cone and a plane that results in a closed curve. The hypothesis describes the conditions necessary for the formation of conical impact cavities and the transformation of the cavities into shallow depressions through a viscous flow process. The four main premises of the glacier ice impact hypothesis are: 1. An asteroid or comet impact on the Laurentide ice sheet ejected glacier ice boulders of various sizes. 2. Seismic shock waves from the impact fluidized or liquefied on consolidated ground along present and past coastlines. 3. Oblique impacts of glacier ice boulders on the fluidized viscous ground created the slanted conical craters. And 4. Viscous relaxation reduced the depth of the cavities and restored the stratigraphy, producing shallow elliptical bays. The glacier ice impact hypothesis does not depend on knowing the exact location of the extraterrestrial impact or the time when the impact occurred. The extraterrestrial impact could have happened at any time during the Pleistocene epoch between 11,700 and 260,000 years ago, when North America had a thick cover of glacial ice. The main objective of the glacier ice impact hypothesis is to determine the effect that an impact would have had on the Laurentide ice sheet and to calculate whether the consequences of the impact could have contributed to the formation of the Carolina bays. It is important to determine that an impact of an asteroid or comet on the Laurentide ice sheet could have ejected glacier ice boulders. It is well known that an extraterrestrial impact on a rocky surface generates a lot of heat, which melts, vaporizes, and ejects pieces of rock. Something similar happens with ice. A hypervelocity impact on ice produces heat that melts and vaporizes some ice, but since ice is a bad conductor of heat and very brittle, many ice fragments are ejected from the impact site. An extraterrestrial impact on an ice sheet would have melted and vaporized great quantities of ice. The ejecta would have consisted of pieces of ice and liquid water accelerated by steam at high pressure. These images show an experiment conducted by Peter H. Schultz from Brown University using NASA's Ames vertical gun. A high-speed impact shatters the ice, and ice chunks are ejected at high velocity, radiating from the point of impact. The radial ejecta pattern is characteristic of impacts and can be observed on the surfaces of planets and moons throughout our solar system. Professor Schultz's experiment provides support for the first premise of the glacier ice impact hypothesis by demonstrating that a hyperspeed impact on ice could have produced an ejecta curtain of ice fragments. The radial pattern of the ejected pieces could account for the alignment patterns of the bays in the East Coast and in the Midwestern states. Having determined that an extraterrestrial impact on an ice sheet could have ejected ice fragments, it is necessary to calculate the characteristics of the trajectories. Because the Carolina bays and the Nebraska bays appear to radiate from the Great Lakes region around central Michigan, it is possible to estimate the distances that the ejected ice fragments would have traveled. The distance to North Carolina is approximately 1,000 kilometers, and the distance to Georgia is about 1,470 kilometers. Using ballistic equations, we can calculate the launch speed, the time of flight, and the maximum height for various launch angles. To reach North Carolina, a projectile launched at 35 degrees would need a launch speed of 3.2 kilometers per second. The time of flight would be 6.3 minutes, and the projectile would reach a height of 150 kilometers above the surface of the Earth. To reach Georgia, a launch speed of 3.9 kilometers per second would be required for an angle of 35 degrees, and the projectile would reach a height of 255 kilometers above the surface of the Earth. All the launch velocities are in the range of 3 to 4 kilometers per second. Since the atmosphere extends only to about 100 kilometers above the surface of the Earth, the projectiles would travel above the atmosphere for most of their flight. It is possible that a substantial quantity of water was ejected along with the ice. Above 35 kilometers from the Earth's surface, the atmospheric pressure is below the triple point of water, and water cannot exist in the liquid state. Any water ejected above the atmosphere or carried along by the ejected ice would have boiled vigorously and produced clouds of ice crystals. For every 100 grams of water in the vacuum of space, the evaporation of 13 to 25 grams is enough to turn the remaining water into ice, depending on the water's initial temperature. This means that up to 75% of the water ejected above the atmosphere would have formed ice crystals. With the additional propulsion provided by evaporation, some ice crystals could have been sent into low Earth orbit, where they would have blocked the light of the sun for many years. This is a reasonable scenario for the onset of a cooling event, such as the Younger Dryas stadia. Knowing the launch velocities of the ejected ice and the size of the Carolina bays, it is possible to estimate the size of the glacier ice chunks that created the bays. The size of any crater depends on the projectile's size, speed, and the angle at which it strikes. Other factors are important, such as the projectile's composition and the material and the structure of the target surface. The University of Arizona has a computer program developed by Professor J. Melosh and Ross Bayer that calculates the projectile size based on the crater diameter and the characteristics of the projectile and the surface. The program estimates that a crater with a diameter of 1 kilometer can be created on sandy soil by an ice sphere with a diameter of 180 meters impacting at 3 kilometers per second. The impact energy of the 180-meter ice ball is calculated to be approximately 1.27 times 10 to the 16th joules, or 3.03 megatons. The application of Newton's laws of motion and the scaling laws relating crater size to kinetic energy allow us to make educated guesses about the proposed extraterrestrial impact. From the ballistic equations, we calculated that the launch speeds of the extraterrestrial ejecta had to be in the range of 3 to 4 kilometers per second. These launch speeds and the size of the Carolina bays made it possible to calculate that a Carolina bay with a diameter of 1 kilometer could have been created by a 180-meter ice ball going at 3 kilometers per second. The energy of the impact would have been approximately 1.27 times 10 to the 16 joules. The inset image shows Yankee Stadium in proportion to a Carolina bay with a major axis of 942 meters. The size of the playing field and all the bleachers of Yankee Stadium measure approximately 180 meters in diameter. This is about the same size as the glacier ice boulder that made the bay. Using these figures to extrapolate to all the Carolina bays, the extraterrestrial impact would have had an energy of at least 6.35 times 10 to the 21 joules. The impact would have ejected 1.5 times 10 to the 12 cubic meters of ice. That is enough ice to cover half of the United States to a depth of half a meter, and perhaps even cause a regional extinction event. The second postulate of the glacier ice impact hypothesis is that seismic shock waves fluidized or liquefied on consolidated ground along present and past coastlines. During the proposed scenario, there were two sources of seismic shock waves: the extraterrestrial impact itself and the secondary impacts from the ejected glacier ice chunks, which, as we calculated earlier, each could have had the energy of 3 megatons. Soil liquefaction is a phenomenon in which a saturated soil becomes like quicksand and behaves like a viscous liquid in response to the applied stress of soil vibrations. Saturated soil occurs when groundwater is close to the surface. Under these conditions, water fills the gaps between the soil grains, and liquefaction occurs when the soil is subjected to a single or repeated change in stress. The vibrations from a seismic shock reduce the friction between the wet soil grains and decrease the load-carrying capacity of the soil and its resistance to shear. Liquefaction has been responsible for extensive damage to buildings and vehicles during earthquakes. These pictures show some buildings that toppled in Japan and some cars that submerged in New Zealand. This image from the U.S. Geological Survey shows the estimated depth to water in North Carolina. The light blue color along the coastline indicates a water table within 5 feet or 1.5 meters from the surface. This coincides exactly with the areas that have Carolina bays. Seismic shock waves travel with a velocity ranging from approximately 2 to 8 kilometers per second. Primary compression waves, called P waves, travel at 5 kilometers per second in rocks such as granite. The seismic waves generated by an extraterrestrial impact in the Great Lakes region would have taken from 3 to 5 minutes to reach the coastal areas of the United States. The shock waves would have fluidized the surface, and when the ejected ice reached its target 6 to 9 minutes after the extraterrestrial impact, the projectiles would have hit a surface liquefied by the seismic shocks. In Nebraska, the bays are also found in soil that is close to the water table. This image from the University of Nebraska at Lincoln shows the depth to water in several shades of blue. Many bays can be found in the area with the light blue color in the floodplain of the Platte River, particularly in Phelps and Kearney counties. The fact that the Carolina bays in the East Coast and in Nebraska occur in soil that is close to the water table and has the potential of being liquefied by seismic shocks suggests that this characteristic was important in the formation of the bays. It is important to differentiate extraterrestrial impacts from impacts at ballistic speeds. Asteroids have speeds of approximately 14 kilometers per second, and comets have speed of around 45 kilometers per second, whereas ballistic speeds are usually substantially less than the Earth's escape velocity of 11.2 kilometers per second. A high-speed impact starts with a contact and compression stage in which the projectile is destroyed and transfers its kinetic energy almost instantaneously to the target surface in an expanding hemispherical shock wave. In the excavation stage that follows, material is vaporized, melted, and displaced from the point of impact to form a bowl-shaped crater with a raised rim. The force of gravity takes over during the final modification stage, and the ejected material falls to the surface, creating ejecta rays or inverted flaps. Molten minerals may collect at the bottom of the crater. The crater walls may become unstable and slide down into the cavity. The high pressures from impacts of comets and asteroids produce planar deformation features in mineral crystals, and the impact site will contain fragments of the meteorite and chemical elements that are more common in space rocks than in the Earth's surface. Impacts at ballistic speeds on hard surfaces have similarities to high-speed impacts, but they do not produce the high pressures that deform mineral crystals. A projectile traveling through a viscous medium creates a conical shock wave, and it is eventually stopped by friction. Impacts on viscous surfaces with low elasticity produce conical cavities that are gradually remodeled by gravity. This image shows the conical shock wave created by a bullet in air and the corresponding conical cavity made on modeling clay. The third postulate of the glacier ice impact hypothesis is that oblique impacts of glacier ice boulders on the fluidized viscous ground created slanted conical craters. This mechanism is proposed as the explanation for the elliptical form of the Carolina bays. The geometrical definition of an ellipse is the shape resulting when a cone is cut by an oblique plane. For this reason, ellipses are called conic sections. For conical cavities, the eccentricity of the ellipse depends on the angle of impact, and the size of the ellipse is determined by the energy of the projectile. A large projectile will create a large cavity, and a small projectile at the same speed will create a small cavity, but the aspect ratios of the ellipses will be the same as long as the projectiles hit at the same angle. This correlates well with the observation that small and large Carolina bays have similar eccentricities. Relating the elliptical shapes of the Carolina bays to conic sections makes it possible to use mathematical formulas to determine the angle at which the ice boulders impacted the surface. Equations from forensic science relate the width-to-length ratio of an ellipse to the sine of the angle of impact. For most Carolina bays, the angle of impact corresponds approximately to 35 degrees. The equations also make it possible to calculate the position of the tip of the conical cavity, which is the location at which the ice projectile would have stopped. This mathematical analysis can facilitate geological exploration looking for stones that may have been carried within the glacier ice. The task will still not be easy, since some of these glacier chunks may have buried themselves to depths of over 300 meters in base with a major axis of 1 kilometer. These are the properties of oblique glacier ice impacts at ballistic speeds on liquefied ground. The projectile leaves no meteorite fragments or siderophile elements because it consists only of terrestrial ice. There is no shock metamorphism because the impact speeds of 3 to 4 kilometers per second are too slow to produce the pressures generated by impacts of asteroids or comets. The impact cavity is deeper at the terminal end due to the oblique impact. The overturned flaps from the impact create raised rims. The elliptical shape is a mathematical conic section. The terminal end of the conical cavity can have a higher rim as material is pushed in the direction of travel. The projectile disappears when it melts, leaving no trace. Viscous relaxation decreases the depth of the cavity, creating a shallow bay. All these characteristics correlate well with the attributes of the Carolina bays. The following section describes some experiments that show the creation of conical cavities and their transformation into shallow depressions. The experiments also clarify how overlapping bays are created. Here is a short video of an experimental impact. Do not blink or you will miss it. Most of the literature about terrestrial impacts has focused on impacts on hard surfaces that produce bowl-shaped craters. Also, there are many examples of impacts on liquids where elastic behavior and surface tension are major forces. Impacts on viscous surfaces with low elasticity have not received much attention, but their study is essential for understanding the formation of the Carolina bays. These images show the conical cavities created by impacts of ice projectiles on a mixture of clay and sand with the consistency of mortar. The target surface retains the conical shape of the shock wave created by the projectile. The material that is displaced by the passage of the projectile creates overturned flaps. These conical structures are later modified by flow of the viscous target material under the influence of gravity. This image shows the overturned flaps created by the impacts. One of the characteristic features of impacts is that the material adjacent to the rim of the crater usually folds over under the influence of gravity, creating a raised crater rim with inverted stratigraphy. The boundary layer is highlighted in the image on the right. Finding evidence of inverted stratigraphy in the rims of the Carolina bays would help to confirm their impact origin. Raised rims are a common feature of all the Carolina bays. This image shows some of the raised rims in the Carolina bays and an illustration of the model proposing that the raised rims correspond to the overturned flaps created by impacts. The center of this image shows 3 large overlapping bays. The mathematical regularity of the elliptical Carolina bays with their particular eccentricity has been largely dismissed by proponents of wind and water formation processes, but the regular elliptical shape is an important feature of the bays. It would be difficult to conceive of a substrate dissolution or wind process that could stop when the perfect width-to-length ratio is achieved, whereas this is fairly automatic for impacts at 35 degrees on viscous ground that create predictable conic sections. Overlapping bays can be modeled by adjacent impacts, and the overlaps indicate the sequence in which the impacts occurred. Any bay that overlaps another one was created later chronologically. In this example, the central bay with a complete elliptical shape was the last one created. The fourth postulate of the glacier ice impact hypothesis is that viscous relaxation reduced the depth of the cavities and restored the stratigraphy to produce the shallow elliptical bays. Viscous relaxation is a slow plastic deformation process powered by the force of gravity that decreases the vertical dimension of the features of a landscape. These photographs show how conical cavities become shallow depressions and how the overturned flaps become raised rims as the force of gravity levels the surface. The photographs also illustrate that adjacent conical impacts are transformed into overlapping bays. Examination of the Carolina bays has shown that the ground beneath the bays is not distorted as is usually the case for extraterrestrial impacts. This has generally been interpreted as an indication that the bays were not created by impacts. However, the excavation phase of an impact on a viscous surface is not an explosive event like that produced by a hypervelocity impact. A projectile impacting a viscous surface penetrates the medium and parts it in a plastic deformation that can be partially reversed by viscous relaxation. This image illustrates a reconstruction of the ground by the flow of the viscous medium. The deeper layers of the cavity, which are under the greatest pressure from the force of gravity, flow faster, causing the cavity to fill from the bottom up. As the process continues, the depth of the cavity is reduced until the gravitational force causing the flow cannot overcome the frictional resistance of the medium. The process of viscous relaxation converts a conical cavity into a shallow depression. These photographs show an experiment that demonstrates stratigraphic restoration. A viscous target surface was prepared with a red layer below the surface. The top left image shows the conical cavity made by an ice projectile that crossed the red layer and dragged along some of the red material. The image on the top right shows the reduction of the depth of the cavity from the bottom up by centripetal lateral flow. At this stage, the projectile has already been covered. As viscous relaxation continues, the lateral flow of material reconstitutes the red layer until it is no longer visible. The images also illustrate the transformation of the overturned flaps created by the impact into raised rims around the final shallow cavity. This experiment provides a good model for the creation of elliptical bays with raised rims. One of the arguments that has been used against the contemporaneous formation of the Carolina bays from an extraterrestrial impact is the fact that the terrains where the bays are found have dates that differ by thousands of years. It would be impossible for the bays to have resulted from a single event if they were formed at different times. Analysis of the bay locations by optically stimulated luminescence, or OSL, has produced dates from 12,000 to 140,000 years ago. OSL dating estimates the time since the last exposure to sunlight for quartz sand and similar materials. Natural radioactivity in the Earth causes electrons to become trapped in the crystal structures of buried quartz. OSL is able to free the trapped electrons and produce luminescence in proportion to how long the quartz has been buried. Exposure of quartz to sunlight eliminates the trapped electrons and resets the clock of the luminescence signal. The impact experiments on a viscous medium have demonstrated that only the surface area of the conical cavity is exposed to light. The rest of the target material is parted and then reconstituted by viscous relaxation without additional exposure to light. If all the target material had been mixed and exposed to sunlight at the same time that the bays were created, OSL would be an adequate method for testing the age of the bays, but this is not the case. The stratigraphic restoration by viscous relaxation leaves a subsurface unaffected by sunlight. Consequently, the OSL dates reflect only the age of the target terrain, but not the age when the bays were formed. Using OSL to determine the age of the bays is inappropriate, just as it would be inappropriate to try to determine the time when Stonehenge was built by measuring the age of its stones. Dissociating the date of the terrain from the date of the structures makes it possible to propose that all the Carolina bays could have been created contemporaneously. Other methods of dating the bays, such as determining the rate of erosion, may be more appropriate. The glacier ice impact hypothesis proposes a mechanism for the formation of the Carolina bays from oblique impacts of glacier ice on the seismically liquefied surfaces of the coast and the Midwest. The slanted conical cavities from the impacts became shallow elliptical depressions through viscous relaxation of the substrata, and the overturned flaps from the impacts became the raised rims of the bays. Although the site where the extraterrestrial impact occurred has not been found, there are two ways in which the glacier ice impact hypothesis can be confirmed. The first one is to find stones that may have been carried within the glacier ice to the Carolina bays. These stones would be found at the point where the ice projectile finally stopped, toward the terminal end of the elliptical bay at the depth approximately 1/3 the length of the bay. Finding the glacier stones is not going to be easy, since not every glacier chunk would have carried stones. The second way to prove that the Carolina bays were made by impacts is to look for inverted stratigraphy in the rims formed from the overturned flaps. This is also going to be difficult because the rims are not very thick and the roots of vegetation and erosion may have destroyed some evidence. Using the ballistic equations, it is possible to reconstruct the timeline of the events proposed by the glacier ice impact hypothesis. At T-0, an extraterrestrial object impacts the Laurentide ice sheet. The impact fractures the ice sheet and melts and vaporizes large quantities of ice. 2 seconds after the impact, seismic shock waves radiate at 5 kilometers per second from ground zero. 20 seconds after the impact, the water and glacier ice boulders ejected at 3 to 4 kilometers per second rise above the atmosphere. At T plus 30 seconds, the water ejected above the atmosphere turns into ice crystals that go into low Earth orbit. 4 minutes after the extraterrestrial impact, the seismic shock waves reach the Carolina coast and liquefy the sandy terrain near the water table. 7 minutes after the impact, the ice boulders re-enter the atmosphere and start crashing into the ground accompanied by sonic booms. The ice boulders penetrate the liquefied ground, creating conical cavities. Ice striking solid ground shatters upon impact, covering the ground with ice pieces. The saturation bombing by the huge ice boulders kills fauna and destroys their habitat. By 10 minutes after the extraterrestrial impact, the ice bombardment had stopped. The solid ground was covered with half a meter of ice pieces, and the fluidized ground was covered with conical cavities that were transforming into elliptical bays. 20 minutes after the extraterrestrial impact, all was quiet again as the sonic booms became inaudible. From this time, the ice crystals in low Earth orbit diminished the light of the sun, and the ice pieces that covered the ground increased the albedo of the Earth, triggering a cold event. Although the events proposed by the glacier ice impact hypothesis could have occurred at any time during the ice ages in North America, the late Pleistocene, 12,900 years ago, provides the best fit. This is the time of the onset of the Younger Dryas cooling event, the time of the extinction of the North American megafauna, and the disappearance of the Clovis culture. Some scientists have proposed that the large mammals that inhabited North America, such as the saber-toothed tiger, the giant short-faced bear, and the mammoths, disappeared as the result of climate change or by overhunting by the newly arrived human population from Asia. However, if the Carolina bays were made by impacts of glacier ice, the heavy bombardment would have had catastrophic environmental consequences for the eastern half of the United States. It is important to determine the mechanism by which the Carolina bays were formed to really understand the history of North America. Much of the research on the Carolina bays has focused on geology, ecology, and the soil characteristics of the bays. Research on the theories of the origin of the bays has decreased substantially since it was established that the bays could not have been the result of extraterrestrial impacts. The glacier ice impact hypothesis opens new areas of research, such as trying to identify inverted stratigraphy in the rims of the bays and the search for glacier stones that may be buried within the bays. Other research topics of importance are identifying the point of origin of the glacier ice projectiles, determining the angle of the impacts that created the bays to characterize the shape of the ejecta curtain, and measuring bay sizes to estimate the energy of the extraterrestrial impact and the volume of ice ejected. Lastly, it may be beneficial to develop computational models of the hypervelocity impacts on ice sheets and of viscous relaxation of conical cavities. The bibliographic references for the background material about the Carolina bays are contained in the book Killer Comet: What the Carolina Bays Tell Us, available from Amazon. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.